This is a study of energy changes. The title for this is called Energetics. It is second term, second topic, grade 11. The assessment criteria for this unit is as follows. You should understand and be able to define enthalpy and enthalpy change. You should be able to understand that chemical reactions involve the making and breaking of bonds and the subsequent energy changes. You should be able to learn how to estimate delta H for reactions. You should be able to determine simple enthalpy changes experimentally and calculate enthalpy changes from provided experimental data. And you should be able to understand Hess's law and be able to use it to calculate enthalpy changes. Delta H, enthalpy. Enthalpy is heat content, or the amount of heat absorbed or released when a bond is broken and then when it is remade again in a different form. The amount of enthalpy is called delta H. When we talk about the delta H of a reaction, we're talking about the reactants breaking bonds, going to their component elements, and then reform into another composition with that subsequent energy. The delta H of a reaction is the delta H's of the products minus the delta H's of the reactants. There are many delta H's: combustion, formation, heat of reaction, and all are looked at as heat content. You see on the picture on the right-hand side of the screen a number of average bond enthalpies. Notice there is no sign attached to these bond enthalpies. These bond enthalpies describe the amount of energy needed in kilojoules per mole to make or break a specific type of bond. A carbon-carbon single bond is 348 kilojoules per mole. A carbon-carbon double bond is 614 kilojoules per mole. Note that these are averages and done over a wide range of different types of molecules. Now you can find the enthalpy or the delta H of a reaction by looking at a balanced chemical equation and determining which bonds are broken and which bonds are remade. In the example you see on the screen, one carbon-oxygen bond and two oxygen-hydrogen bonds were broken. The number of bonds created were two carbon-oxygen bonds and one hydrogen-hydrogen bond. Note in this case, all reactants or products are in the same phase, in this case, gas. If not, then you must take into account a delta H for the change from the gaseous to the liquid state, or the solid to the liquid state, and so on. Measuring enthalpies experimentally is often done through the study of calorimetry. Calorimetry is the study of the specific heat energy that is created in reactions through the heating of another substance, most oftentimes water. For example, if you were interested in to know the energy required to raise a mass of a metal a specific amount of degrees, you could find that energy by using the formula mc delta T. You've done this in grade 9 and grade 10 chemistry. The underlying principle of Hess's law states that if a reaction can take place by more than one route, and the initial and final conditions are the same, then we can compute this. Basically, what Hess's law allows us to do is make the study of delta H's an algebraic comparison. We'll do a number of examples of these in our class. The following video will help you get an idea of how to manipulate enthalpy reactions.
Hello and welcome to the Chemistry Solution. This tutorial is on Hess's law. Remember that enthalpy is a state function, and that means it depends only on the current state of the system. That means that the enthalpy change, or delta H for a reaction, depends only on the initial and final conditions and not the path taken. And so whether a given reaction occurs in one step or in many steps, the enthalpy change remains the same, and this is the basis for Hess's law. Hess's law states that the enthalpy change associated with a reaction carried out in multiple steps is equal to the sum of the enthalpy changes for each individual step. So let's look at an example. Calculate delta H for the following reaction. 2 carbon monoxide plus O2 goes to 2 carbon dioxide. And we'll calculate delta H for this reaction given the two reactions below and their delta H values. So the first step to do this is to manipulate the given equations so that they most closely resemble the equation of interest. So let's look at our first equation. In the reaction of interest, carbon monoxide is on the reactant side. And of the two equations given below, you only see carbon monoxide in one of these equations, and it's on the product side. So what we're going to need to do is to flip this equation around so that carbon monoxide is on the reactant side. So we'll write the equation below, except we'll flip it around. So here we have 2 carbon monoxide going to 2 carbon plus O2. And because we flipped this reaction, we need to flip the sign on delta H. So remember, the delta H value for a reaction written in the opposite direction is of the same magnitude but of opposite sign. And so if we flip the equation, we flip the sign on delta H. So if 2 carbon plus O2 gives us 2 CO and the delta H value is negative 221 kilojoules per mole, then 2 CO going to 2 carbon plus O2 has a delta H value of positive 221 kilojoules per mole. Looking at our reaction of interest, I see that there are 2 moles of CO2 on the product side. And when I look down at our given equations, I see only one of the equations have CO2, the second one. It is on the product side, but there's only 1 mole of CO2 in this reaction. And so for this equation, I need to multiply it by 2. So that I have 2 moles of CO2, so it more closely resembles the reaction of interest. And when I multiply the reaction by 2, I need to multiply the whole equation by 2. And I think it helps to draw parentheses around the entire equation. So this gives us 2 carbon plus 2 O2 gives us 2 CO2. And again, I want to perform the same operation on delta H as I did on the equation. So if I multiplied the equation by 2, I need to multiply the delta H value by 2. So if the reaction carbon plus O2 gives us CO2 had a delta H value of negative 393.5 kilojoules per mole, then the reaction 2 carbon plus 2 O2 gives us 2 CO2 has a delta H value of negative 787 kilojoules per mole. So here I've written my two new equations that I modified to more closely resemble my equation of interest. And what you're going to do now is add these two equations together, keeping everything on the reactant side on the reactant side, and everything on the product side on the product side. So in my new equation, I have 2CO plus 2C plus 2O2 gives me 2C plus O2 plus 2CO2. And because I added the reactions together, I'm going to add the delta H values together. So the delta H value for this equation is negative 566 kilojoules per mole. But you'll notice that I have some compounds that are the same on both the reactant side and the product side. And so anything that's the same on both sides of the reaction arrow can be canceled out. So I can cancel out my 2 moles of carbon on both the reactants and the product side. And I can also cancel out the 1 mole of O2 on the product side with 1 mole of O2 on the reactant side, leaving me with the final equation 2CO plus O2 goes to 2CO2. And the last thing you need to do is to double check that this equation matches your equation of interest.
Here are some questions to start your thinking. How can you determine if a reaction is endothermic or exothermic based solely on the delta H? Hess' law makes the determination of heats of reaction a simple math exercise. What physical conditions need to be examined in any Hess law problem? And thirdly, can combustion reactions be solved using Hess's law? What is the problem with using Hess's law and combustion?